Welcome to Biogas Basics. My name is Jürgen Kube. In the last presentation, we discussed rheological properties of digestate, shear thinning fluids, and the impact of yield stress. This presentation will be a bit more hands-on, and I will introduce different pump types used in the biogas industry, make some recommendations when to use which pump type, and highlight installation and instrumentation requirements. The next presentation will then show how to calculate pressure drop in digestate and slurry pipelines, but first, let's discuss pumps. And now, pictures. Progressive cavity pumps are the workhorses of the AD industry. They are used for medium and high viscosity applications and media with yield stress. Progressive cavity pumps can handle fibrous material. The pump is driven by an electric motor, which is connected via a gearbox to the bearing, which is sealed against the substrate-filled part of the housing. A double cardan joint connects the drive shaft to the rotor, which is made from a hard steel. The end of the rotor moves in a circular motion in the stator made from an elastomer or rubber. Between the rotor and stator occurs a cavity that fills with fluid and progresses along the axis of the pump to the discharge side, giving the pump its name. I want to talk about the correct installation of a progressive cavity pump as well. The pump pumps from the digester through two valves. Generally, each digester outlet below the liquid level should have two valves. Here a manual and an automatic knife gate valve. Between the two valves should be a spool piece. Sometimes the valves are installed flange to flange, but if a valve is blocked, for example by a piece of wood, the chances are high that both valves block at the same time. A spool piece between the two valves prevents this. The pump is fed via the suction pipe. The suction pipe should be as short as possible. It should have a large diameter to minimize the pressure drop on the suction side of a pump. The suction side should have no high points or swan necks that can accumulate gas. Otherwise, some of the pumping energy is used to irreversibly compress and expand biogas bubbles in the pipe. Needless to say is that the pump should also be at a low point so it can use the hydrostatic pressure of the tank it pumps from. The discharge side of the pump can have a smaller diameter. Pressure drops on the discharge side can be overcome by the pump but are critical on the suction side. Progressive cavity pumps can pulse, especially when the stators are worn, and some fluid can flow back from the discharge to the suction side. Compensators help to minimize pulsing and separate vibration from the pump from the pipework. A simple trick to minimize pulses on the discharge side is a 1 meter long vertical and capped pipe on the discharge side, which will fill up with biogas and acts as a pulsation dampener. Each progressive cavity pump should have a dry run protection. This is a thermocouple inserted into the stator. If the pump runs dry, the friction between rotor and stator will heat up the stator, and the thermocouple will pick up the temperature rise and stop the pump. At the outlet of a progressive cavity pump and upstream of the first valve is a pressure sensor. If the sensor picks up a high pressure, it stops the pump. Progressive cavity pumps are positive displacement pumps, meaning that they always transport the same volume per rotation, almost regardless of the pressure on the discharge side. If the discharge side is blocked, this can lead to high pressure spikes in the pipework, which can easily crack the pipework or pump housing or push flanges apart. A flow meter is a nice to have. If the pump is running and the flow meter shows no flow after a lag time of a couple seconds, the pump stops. Most pumps also have a thermistor in the motor windings, which senses overheating if the pump motor experiences too much torque, and a max runtime, in case there is a fault in the PLC and a sensor malfunctions that would normally cause the pump to stop, for example a level sensor in a tank that the pump discharges into. Progressive cavity pumps are large and require good maintenance access. It is recommended to install the pump onto a plinth or pedestal, so it is possible to put a pallet truck under it. Make sure that there is a small piece of pipework with a flange at the outlet, which can be removed when the pump needs maintenance. I have seen progressive cavity pumps with 20-meter welded pipes on the outlet, which are a nightmare to maintain. Most important, make sure that there is enough space in front of the pump. This is required when the stator needs changing and is pulled out at the discharge side. In this picture here, the valve at the discharge side can be closed and the short pipe piece removed, and the stator can be pulled out of the pump without any pipeline in the way. Above the pump, and not seen in the picture here, is an I-beam with a chain hoist to lift the pump up and transfer it to a small wheel loader. It is also recommended to place a drain near the pump. This area will get messy during pump maintenance, and in case any civil engineers are listening, the drain must be at the lowest point of the room. Rotary lobe pumps are positive displacement pumps similar to the progressive cavity pumps. Rotary lobe pumps comprise two rubber or steel lobes that rotate and move fluid by trapping it in cavities between the lobes and the pump casing. The two lobes are aligned in parallel, giving the rotary lobe pump its typical O-shaped silhouette. Rotary lobe pumps cannot handle fibers very well and wear quickly if they pump fibrous digestate. Their preferred application is lower viscosity and higher flow rates digestates compared to progressive cavity pumps. They are best used for pumping liquid feedstocks and separated digestate. Rotary lobe pumps are easier to maintain than progressive cavity pumps due to smaller size, and the fact that the front of the pump can be simply removed but need more maintenance as they move faster and seals and bearings are more exposed. As positive displacement pumps, they should be equipped with a pressure sensor to protect the pipe system from overpressure in case they pump against a closed valve. Like progressive cavity pumps, rotary lobe pumps are self-priming, meaning that they can suck gas for a short period until the suction pipe is filled with liquid. However, rotary lobe pumps are very sensitive to dry running and struggle when the suction pipe is filled with biogas. Rotary lobe pumps do not have a stator that can be equipped with a thermocouple, so a flow meter makes sense to protect against dry running. On biogas plants, centrifugal pumps are mostly used in warm water systems and for pumping surface water. Centrifugal pumps are dynamic pumps. They rely on the kinetic energy of an impeller to pump a liquid. They are not self-priming, meaning if the suction side is filled with gas, the pump will not pump but run dry. Centrifugal pumps can be made self-priming by installing a non-return valve in the suction line which prevents liquid from running from the pump. But non-return valves should not be installed in substrate systems of biogas plants as they block, break or leak in digestate. The main applications for centrifugal pumps on biogas plants are in the hot water system and for drainage, though they can be an alternative to rotary lobe pumps in high-flow, low-viscosity digestate applications. Centrifugal pumps can be equipped with chopper blades combining a pumping and maceration step. Unlike positive displacement pumps, the volume flow of a centrifugal pump depends strongly on the discharge pressure. This means that pumping against a closed valve will not lead to pressure spikes, but it can still damage the pump and should be avoided. One special property in biogas applications is that centrifugal pumps can fill with biogas when they pump digestate with entrained biogas bubbles. Digestate is supersaturated with dissolved CO2, and the high shear forces in the centrifugal pump will transport dissolved gases to the gas phase and coalescence gas bubbles. The lighter biogas can accumulate in the eye of the impeller, blocking the center inlet while the heavier liquid rotates around the circumference of the body where the outlet is located. This can reduce the volume flow of the pump and gaslock the pump. Centrifugal pumps used for digestate often have special impellers, which are less efficient than impellers for gas-free fluids like water, but can deal better with gas accumulation. When using centrifugal pumps for digestate, speak to the pump supplier to select the correct impeller for this application. If pumping digestate, centrifugal pumps must be vented properly and operated with a high suction pressure and short suction lines with no high points, a recurring theme for all pumps handling digestate. Some less common pump types are also used in the AD industry. Peristaltic pumps use a hose to pump digestate. The hose is squeezed by two wheels on a rotor. The hose must be lubricated and cooled. While this pump is not very efficient, it is resistant to wear as the hose is the main wear part, which can be replaced easily. The pump is quite large and is sold as a high capex, low opex alternative to rotary lobe and progressive cavity pumps. It is best used for medium pressure and flow applications of fibrous materials with yield stress. The most common application for piston pumps is pumping concrete. The pumps comprise one or two pistons, then push the material into the pipe system using a hydraulic drive. They can produce extreme pressures but get expensive very quickly for higher flow rates. In the AD industry, piston pumps are mostly used in high solids biowaste fermentations to pump feedstock slurries or high viscosity digestates for biowaste CSTR or plug flow reactors. Human ingenuity has created many different pump types which are used and can be used in the AD industry. This list is not conclusive. For example, ball valve, membrane pumps, centrifugal screw, or axial flow pumps are used in some niche applications, but I have focused on the most common pump types here. When selecting pumps, I use this qualitative diagram. It shows the viscosity of the medium, i.e. its resistance to shear over the required flow rate. For high flow, low viscosity applications, centrifugal pumps are often best suited. As the medium will become more concentrated and the viscosity increases, the maximal flow required typically decreases. The next type of pump are rotary lobe pumps, better suited for fiber-free fluids with entrained gas bubbles, but less suited for fiber suspensions or suspensions with grit. Progressive cavity pumps can typically pump up to 100 cubic meters per hour before they become too large to maintain. They offer a good mix of volume flow, ability to work with high viscosity, and wear resistance. Peristaltic pumps have a similar behavior to progressive cavity pumps. Piston pumps are used for low-flow, high-pressure application around feeding solid rich feedstock suspensions. A later part of this mini-series deals with feeding systems and describes pumps for feedstock, digestate suspension, and dilution requirements. For most fibrous digestate pumping applications, a progressive cavity pump is the preferred choice. In almost all applications, the medium can be diluted enough so that this pump can handle it. Only in cases where dilution is not possible or wanted, for example when feeding plug flow reactors, piston or ball valve pumps should be used. Rotary lobe pumps should be used further downstream or in fiber and grit-free applications. Centrifugal pumps are best used for water or other high-flow, low-viscosity applications. Let's conclude. We started with the progressive cavity pump, which is a good all-rounder on biogas plants. It is a positive displacement pump, and those pump types should not pump against a closed valve, or things will start to break quickly. I showed the correct installation and instrumentation of this pump and highlighted the requirements for good maintenance access. The rotary lobe pump is used for higher flows and lower viscosities compared to the progressive cavity pump. Rotary lobe pumps have been used in agricultural slurry applications, but are less suited for fiber or grit-rich fluids. They excel in applications of gas-saturated fluids. As positive displacement pumps, they are self-priming, at least as long as the lobes are not too worn. Centrifugal pumps are used for even higher flows and lower viscosities. They are dynamic pumps and can pump against a closed valve for a short period without damaging the pipework. Centrifugal pumps can be prone to gas accumulation in the middle of the pump and require special impellers for digestate applications and can be equipped with macerator blades to act as chopper pumps. I also briefly mentioned other pump types like piston, membrane and ball valve pumps that are used in high solids, low flow applications, mostly around feeding at low dilution requirements. Thank you for making it to the end of the presentation. It focused on practical tips for pump selection and installation. The next part of this mini-series will again be a bit more theoretical and summarize all methods required to calculate pressure drops of shear thinning digestate in pipes. I hope you learned something new, and I see you in the next episode of Biogas Basics.